Okay, welcome to another lecture of cryptanalysis, and in particular another lecture on cryptanalysis of symmetric key encryption schemes. Today we're going to look at the second very big statistical type of attack, namely linear cryptanalysis, similarly famous as differential cryptanalysis and similarly old as differential cryptanalysis. So what's the plan for today? Let's see. So first I want to introduce the basic concept that is at the bottom of linear cryptanalysis, namely the concept of linear approximations. This is going to be something similar to differentials and differential characteristic, but with a different property. And again, afterwards, like last time we looked at differential cryptanalysis, we're going to then have a look at how can we use these properties to actually recover the key. And finally, we're going to look at some examples of actual ciphers, how we can find such linear approximations for these ciphers, or say something about how good they are, and how we can apply these concepts essentially. But as usual, before we go into the details, let's have a recap quiz and also an announcement ahead of time. After this last part, we're going to, of course, have a look at the second assignment example, which is released today. So this will be at the end of the lecture. Now let's have a look at that quiz. I saw some of you already joined earlier. So let's see. As usual, this is not about last week's lecture, but about 2 weeks ago. Based on the statistics I see here, it might be that some of you have had some latency issues and are currently not live. So maybe you want to check that again to see whether you're a few seconds behind or actually live. In particular, I saw more people than that waiting earlier before the lecture started, so I hope they can join in a moment as well. Okay, it looks like not much is happening, so let's start the quiz anyways with a bit fewer players than usual. So let's see. Which type of attack is differential cryptanalysis? Is it a known plaintext attack, a statistical attack, an algebraic attack, or a ciphertext only attack? Only one of these is correct. Yes, you're right. It's indeed a statistical attack. So to clarify here, these are all not mutually exclusive. So these two are sort of opposites, the statistical attack and the algebraic attack. But differential cryptanalysis is indeed statistical, which means it's about counting how often things happen and how often they should happen and looking if we're somewhere close. Whereas algebraic attacks are usually about deterministic properties. So we don't have any probabilities involved right here. These two are on a separate axis, so to say, and indeed differential cryptanalysis is neither ciphertext only nor known ciphertext, but we actually need to choose our ciphertext because we want to have specific differences. This is, by the way, going to be different for linear cryptanalysis today. So let's look at the next one. Which one of these is not a valid differential for the AES? By this here I mean lots of Fs, so all bits set to 1 and all bits set to 0 at the output of full AES, or all bits except the last 4 set to 1 in the input and the output, or all bits 0 at the input and all at the output. Okay, So indeed, this one here is correct, because it's not possible in the AES that I look at two input plaintexts which have a difference, but where the ciphertext is identical. This would be impossible to decrypt if the AES had such a differential, because it would mean that two different plaintexts map to the same output. That's not possible. So indeed, this is not a valid differential. This one here is most likely valid. If you could prove that it's not valid, you would have found a very big scientific discovery about the AES. And finally, we have that one here. This was a bit of a trick question. So this is all zeros to all zeros. This is indeed a valid differential characteristic, or a differential, in the sense that it's actually possible that it happens, because if we have identical inputs, the outputs are also identical. However, it's not a useful differential. So we usually call it the trivial differential and don't use it for attacks. So in attacks, we've always excluded this case, but it's still nevertheless actually a valid differential. Okay, third question. What can you say about the probability of a differential characteristic versus the corresponding differentials? Are the two, so of a characteristic and of a differential, always the same? Or can the characteristic have a lower probability than the differential, or can it have a higher probability than the corresponding differential? Here, for the first time, the majority is not right. So they're definitely not guaranteed to be the same. They can be. This happens if the one differential characteristic we're considering is the only one that contributes to that differential. But there might be several different differential characteristics that lead to the same differential. And if that's the case, then their combined, summed probability makes up the probability of the differential, which means the differential might have a higher probability, or in other words, the probability of the characteristic is lower than that of the differential, and not higher. Which key is the correct one in a differential attack? How do we recognize it? Is it probably the one that received the most upvotes? Is it definitely the one with the most upvotes? Or is it the one that got exactly 2 upvotes? Absolutely correct. It's most likely the one with the most upvotes in case we have collected sufficient data. If we do not have sufficient data, this might not be the case, so there might be an incorrect key that by chance has a higher upvote count. So it's not guaranteed, but most likely with this suitable attack setup. Which key is the correct? Oh, we had that already. It appeared that for some reason it called the same question again. Well. Let's see if the evaluation is correct now, because on my phone the right question displays, but here we have the wrong one. So apparently they're not in sync. Probably you got the other question displayed, which means that probably what's displayed here is incorrect, but what you see on your phones is actually correct. So the question was about how many pairs you need in an attack with a characteristic of probability P. And if I remember correctly, this last answer here on your phones is actually the correct one, because it said that the probability is approximately 3 times 1 divided by P. So in other words, we inverse the probability of the characteristic and then take about 3 times as many for good measure, and that's correct. If I remember correctly, this one was 1 divided by P to the power of 3, which is not correct. This one here was, I think, 1 divided by 3 times P or so, which is not correct because it's too few ciphertexts. So the right order of magnitude, but still too few. And I guess for the final evaluation, it's hopefully going to be displayed correctly. So let's look at the last question. What's the lowest possible maximum differential probability of an n-bit Sbox? Is it 1/2 maximum differential probability, or is it 1 divided by 2 to the power of n, or is it 2 divided by 2 to the power of n? Okay, this middle one here, this would correspond to the case that we have an Sbox, and if we look at its differential distribution table, this table has all ones in all rows and columns. Then 1 divided by 2 to the n would be the maximum differential probability. However, this is actually not possible, because whenever we have one solution for a particular differential, then there must always be a second solution, which is the first solution XOR the input difference that we're looking at. So if you remember, when we looked at DDTs, all the entries were always even numbers. And in the best case, these are all 2s, in which case we have this probability here. Okay, let's look at the leaderboard and let's hope all the votes were counted correctly. So congratulations to 123 for winning this one. And thanks everybody for joining in. So let's look back at the lecture now. And let's look at the concept of linear approximation and characteristics. So I've chosen this symbol here for this chapter because linear approximations are also called linear trails. And it essentially corresponds to finding a path of linear relations through the cipher. But let's have a look at an overview first. So this attack has approximately the same age as differential cryptanalysis. It was proposed just a few years afterwards by a Japanese cryptographer, Mitsuru Matsui. And he used it to attack the data encryption standard, the DES, and actually succeeded in doing so, and took only 2 to the 47 known plaintext ciphertext pairs for this, whereas the block size of DES would be 64 bits and the key size 56 bits. So this means that this is faster than generic attacks. So this was actually a full round break of DES. And this very quickly made it one of the 2 major attack techniques, and more specifically, one of the 2 statistical attack techniques that much of the current field of cryptanalysis is focused about or derived from. By now there have been many extensions of this attack, many variants which are applicable to ciphers which are secure to the basic version, but still the basic version is a very important criterion whenever you are designing or evaluating a cipher. So what's the basic idea? What we want to do is we want to find an approximate equation about the full cipher. And this equation is supposed to link the plaintext input block, the ciphertext output block, and the key of a block cipher together. And it's supposed to link these in just one equation, an equation of XORs. So it XORs some bits of this and this and this, and this is supposed to be approximately 1 or 0, in other words, more likely 1 or more likely 0. And so we have just a 1-bit equation, and we want to use this as a distinguisher to recover the key. So to recall a bit what sort of cipher we're talking about, it's still exactly the same sort that we also saw last week, namely key alternating ciphers, which take an input block of a certain size, like 128 bits, apply a round, XOR the round key, which is derived from the master key, apply the next round, which is keyless, then XOR the key again, and so on. So we're always again going to talk about this concept of round-based ciphers and assume that the key is XORed in between the keyless steps. And again, these rounds are going to consist mostly of an Sbox layer or nonlinear layer on the one hand, and a linear diffusion layer on the other hand. And to see how similar linear and differential cryptanalysis actually are, let's briefly recall what we saw last week. So in differential cryptanalysis, we had this idea that we looked at two input plaintexts which are very similar. They have a known or a fixed difference of a few bits which are different. And we were interested in following how this difference propagates through the cipher in order to be able to predict whether one particular output difference between the ciphertexts is potentially a bit more likely. And if we had this property, then we could use this for different things. We could use it, if we have this property for most rounds of the cipher, we could use it for key recovery because we could guess a part of the last round key, compute backwards from the ciphertext and check whether our prediction was met. Or we can more directly use it by assuming that the output difference is as we would predict and then trying to get rid of this difference. For example, cancelling it out to get a collision. Now in linear cryptanalysis, the pictures look very similar. So we're again going to look at a property which degrades throughout the cipher, which we try to propagate, but where we never know for sure what happens. But instead of differences, we're going to have masks. We call them linear masks, and they're typically denoted by Greek letters, so I'll mostly be calling them alpha and beta. And these are now not properties of a pair of ciphertext, but just of a single ciphertext. And we'll get to what it is exactly in a moment. But for now, let's just say we have these masks and we try to get a good mask at the output. And if we have that, then we can again use these masks in a similar way as in the differential case. We can guess part of the key and see whether our mask does something useful. Or alternatively, we can also use the mask, which is going to give us a tiny bit of knowledge, well actually one bit of knowledge about the output of the text. And if we know that this output is, for example, combined with some secret or so, then we can use this one bit of knowledge to learn something about this secret. So we can attack the confidentiality of a scheme. And now let's get to what these masks are about. I already said that they are linear equations. And to look at what we mean, let's have a look at not just the full cipher at once, but just at one tiny operation. The tiniest possible operation, which is just a single AND gate. So let's look at an AND gate which has two input bits and one output bit. And let's briefly write down the truth table of this gate. So if either one of the two inputs is 0, then the result of the AND gate is 0, and if both are 1, it's 1. So far, so easy. This is a non-linear function. Now let's try to approximate it with a linear function. Which linear functions can we choose? Well, there are actually exactly 4 linear functions of 2 input bits. That's actually a bit more than you might expect. You might only have been thinking of this linear function, summing everything or XORing everything. But actually, just taking one of the inputs or not taking any input at all is also a linear function. So these are like alternative gates which are linear, which we could have instead of the AND. Let's see now how often these linear functions give the same result as the correct nonlinear function. Let's see. So if I simply guess that the output is 0, then I'm actually correct in 3 out of 4 cases. If I guess that the output is equal to X, then I'm also correct in 3 out of 4 cases. It's a different 3 cases, but still the 0 here, the 0 here, and the 1 here are correct, whereas the 1 here is not correct, should have been a 0. The similar thing happens for Y. The only difference is for the XOR. So the XOR actually turns out to be wrong in most cases. In 3 out of 4 cases, it's wrong. So what does that mean about how we could linearly approximate this function? Does this mean now that we have 3 suitable approximations? Well, actually we've got 4, because we are not limiting ourselves to linear functions only, but we're also considering affine functions. Affine simply means that I can take a linear function, which is linear in the linear algebra sense, and XOR a constant to it. So I can, for example, I take either 0 or 1. I can take either X or X plus 1. I can take either Y or Y plus 1, and so on. And what this means is that if if we look at any of these approximations, they are actually good representations which are correct in 3 out of 4 cases. This one here looks like a bad approximation, but that means it also gives rise to a very good approximation if I simply toggle the result. So if I take x plus y plus 1, because then only the first one here is incorrect and the other ones are all correct. So this means we have 4 candidate approximations, linear approximations of this one gate. And what we want to now do is we want to extend this sort of approximation through the whole cipher so that at the very end I can approximate the complete output or part of the output from the input in a completely linear fashion. But before, again, we go the big step to full ciphers, let's grow just a tiny bit bigger. Instead of one gate, let's look at one Sbox, because this is the nonlinear function we usually care about. So here is an Sbox, which is also, by the way, going to be relevant for your exercises. And this Sbox belongs to a block cipher called present, which looks very similar to the toy cipher we've seen last week. And in particular, it has a 4-bit Sbox, 4 input bits, 4 output bits, and here's the corresponding lookup table. What we now mean by a linear approximation of the Sbox is not actually knowing a completely linear representation for each of these output bits here, but we just want one linear relation. So we want to select some input bits here and some input bits here, XOR them together, and see whether it's 0 or 1. If it's 0, it means the approximation is correct in the sense of the previous slide. If it's 1, it means it's incorrect in the sense of the previous slide. So let's look at one particular selection. Let's pick that bit and that output bit. And what I've done now here is I've now translated this table here, so the definition of the Sbox, just into a binary representation. So each of the 16 possible input values is here, each of the outputs is here. And what we're interested in is whether this bit here, XOR that bit here, XOR that bit here is 0 or 1. Here I've denoted by a check mark all the cases where it's 0. So where the approximation that y4 equals x1 XOR x4 is correct. And an X in the cases where this is not correct. And we see there's again a tendency towards this approximation being correct. So this looks like a good approximation. Probability 12 out of 16 cases. And how do we now get from this representation or this thought process to this mask thing that we're actually going to use? Well, we're just going to have a mask that selects which of the bits we're taking into account in our approximation and which ones we aren't. So the previous example here would correspond to a mask of alpha equals 1001, selecting the first and last bits, and an output mask of 0001. And this is how we can write down our relations. We're going to write it with the help of this inner product here. So the XOR of this mask bit times this input variable, this mask bit times that, blah, 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 XOR together, and the same thing for the output. And so in summary, this equation here can be written like that. Alpha, this alpha here, times the input variable x equals beta times the output variable y, which is the same as the Sbox applied to x. So this is a very compact notation, and the advantage of this is now that instead of writing down all these equations here, I can just represent each intermediate variable by one of these masks. And this is now similar to the way that we wrote down intermediate differences. For example, in the differential lecture, we had, for example, delta x for the difference in x. And here instead we have alpha, we could also say alpha x, for the mask for x. Now, if you read actual papers about this, you will find a ton of different notations for the same thing, unfortunately. So some people write the inner product like that. Some people write the second vector with a transpose because they see it or interpret it as a sort of matrix product. Some people use braces, angled braces. This is more coming from the linear algebra area. Or some people also represent the selection of the bits as a linear function. So they write some linear function L alpha of x. It all means the same thing, so it's usually clear from the context, but be warned, there is quite a chaos of notations, and unfortunately not only of notations, but also of metrics, how we measure how good a characteristic is. We've seen one metric so far. We've counted how many solutions there are. So we've looked how many concrete values of the input satisfy the equation that mask times input value equals output mask times output value. And we counted 12 solutions. We can also translate this into probability. We've done that already. This is simply number of solutions divided by number of all possible input values. What we're actually interested in is, however, not how many are correct, but we're going to try and use this as a distinguisher. So we want to distinguish this approximation here from random. So from a random approximation that's no good. And if we have a completely random approximation or an approximation of a random function, how often will it be correct? It's not going to be always incorrect. Since it's just one bit, it actually has a 50% probability of being right by accident. Any of these equations. So what this means is, what we're actually interested in is not just how large this value is, but how different it is from random. So how different this probability is from 1/2. And this is called the bias. So the bias is simply the probability minus 1/2. It's a value between minus 1/2 and plus 1/2. And the larger its magnitude, the better or the stronger the approximation, the more non-random. So a very good approximation would have plus 1/2 if it's perfect, and a very, very bad linear approximation that's always wrong would have minus 1/2, but that can be also easily translated into a good one by just taking the inverse. Okay, so far I think these metrics all make sense and they're also easy to tell apart. There is, however, one more which turns out to be more useful for computing things. And this is the so-called correlation, which is simply 2 times the bias. Now this looks a bit arbitrary, but we're going to see later why it's useful. The main property here is that the correlation is a sort of normalized version of the bias. So this is always between -1 and +1. And this normalization makes it more useful or easier to calculate with. So let's focus mostly on this correlation in the lecture. And now what do correlation or bias tell us about the quality of a characteristic? I've already said it. If the bias is 0, then the approximation we have is just as good as random guessing. So it's correct half the time, it's wrong half the time, so we don't learn anything from it. If the epsilon or also the correlation is positive, it means it's correct more often than not, meaning this is a good linear approximation. And if it's negative, this is a bad linear approximation, but then by XORing 1, I get a good one again. So both of these cases are interesting for modeling a cipher in linear equations. And now since there is not just one possible mask, but many possible masks, so we can actually consider all possible, so if we look at the picture, all 2 to the 4 possible masks at this stage here, and also 2 to the 4 possible masks here. And we can evaluate each of them how good it is. So in other words, we can look at all linear approximations and check out how good they are. Of course, we want to write down the result in a table, which looks exactly like the differential distribution table, except that the range of the entries is different. So traditionally in the linear approximation table, we write down the number of solutions minus half of all possible values. So yet another metric that I haven't mentioned on the previous slide, but this is what we usually write down. So a 0 means this approximation is correct in exactly half the cases and thus is useless, meaning we can't learn anything from it. So the zeros in this table are just as useless as the zeros in a differential distribution table. The larger the entry here is, the more a linear approximation tells us about the function, because it's either very often or very rarely correct. So these are the ones we want to use for analysis. And again, we can give a name to the largest entry in this table here. It's going to define the strength of our Sbox, for example. Or if this is a larger building block, then of this larger building block. So far we've only looked at all the nonlinear functions, or specifically at the Sbox. But of course the cipher consists not only of Sboxes, but also of linear parts, of linear functions. Now the question is, what are good linear approximations of a linear function, or how do I get them? This sounds like a very easy question, but actually it still probably needs writing down for you to find it out. So if we look at one linear function, like for example mixed columns in the AES or bit shifting in another cipher, then since this is already linear, any other linear function is either the same linear function, which means it's perfectly correct, or an approximation is perfectly compatible with the linear function, or it's incorrect, in which case the truth has an XOR of another variable, or an XOR of other XORed variables, which means there is an additional coin flip in it, which means it's correct in half the cases and incorrect otherwise, so the correlation is 0. So which ones are now the good approximations, or how do I find them? The easiest way to do that is actually to write down the linear function that we're looking at as a matrix multiplication, just like mixed columns, but a bitwise function. And if we then look at any pair of masks A and B, so at any one linear approximation, then the correlation of these two is 1 if and only if alpha is the same as the transposed matrix times beta. Otherwise, this is a bad approximation, and the correlation is 0. So if you're not sure why this is the case, it's probably easiest if you try it out with a little permutation matrix or so to see why this makes sense. So if we're looking at this affine layer, which means it's a linear function plus potentially a constant, then the correlation additionally depends on the constant. So it's either plus or minus 1, depending on that constant. And one specific case of this constant addition that we're interested in is the addition of the key. Okay. So let's have a look at exactly that, at the addition of a key right before an Sbox. So let's look at the same Sbox as previously, with input and output X and Y, but we have an additional key, where one bit is XOR to each of the input bits. So if we now have a linear approximation, it actually takes a more complicated shape. So in particular, if we already know, for example, an approximation of this inner Sbox here, and we want to translate it into an approximation of the values before the XOR and the key, then this correlation is going to involve a mask on the key and a mask on the input, and it turns out it needs exactly the same mask. You can easily see it on this picture here. So if you look at the same approximation as before, first and last input bit and last output bit, then knowing this one input here is the same as knowing the XOR of those two. And since this value is equal to the XOR of those two, I can also replace it by this XOR in my equation. And similarly, I can replace this bit by the XOR of those two. So in other words, if this plus this plus this is correct, then this plus this plus this plus this plus this is also correct, and vice versa. So this means the key, which plays this role of a constant here, also has a corresponding mask in my representation. And I can now either write it down like would follow intuitively here, so I can have all the input related variables on the left hand side and the output on the right hand side, or more interesting, I can bring those to the other side and y to the other side. So what I get then is an equation that looks much more interesting. I learned that some known variables here, known because they are the input and output of my function. Let's assume this is the whole cipher here. And this is equal to an XOR of the key bits. Now, the key is completely unknown, but if I know all of the left-hand side here, then I learn 1 bit of information about the right-hand side. So I get a 1-bit equation about the key, which means I reduce the key space by 1 bit. Okay, that's not particularly impressive. However, we will see a bit later that when I do actual key recovery, I can get much more than this 1 bit of information. So I've now already acted as if this one Sbox would be the entire cipher. Let's get at least a tiny bit closer in that direction by looking not just at one Sbox, but at 2 consecutive Sboxes, each with its own key addition layer. Now this is actually not much more complicated than before. So for example, I can, if I start with the same approximation for the first Sbox here that I already have, and I want to go forward and trace what happens to this bit in a cipher. If I want to express this bit here in my one equation I have, then I can also represent it as the XOR of the key and that next intermediate variable, which means I can replace this in my equation with the XOR of these two. This one I just have to keep there, but this I can in turn replace by an XOR of some of the output variables here if I have another suitable linear approximation. So let's quickly check in the table we saw before. What are suitable masks if I have an input mask of 0, 0, 0, 1? Let's go back. So 0, 0, 1 is exactly this line here. What I see now is I can have 5 as a good approximation, actually a very bad one, but as we already saw, we can translate it into a good one. Or I can take 7, or I can take D or F. And all of them are actually equally good. Now, since 5 has the fewest bits, it might be the most attractive one. So let's just adopt that for the moment. And I think that's indeed what I did here. Yes, here I took the 5 as well. So now I can replace this variable by the XOR of these two. Or in other words, I've combined this equation for the top Sbox and this equation for the bottom Sbox, both of which use this intermediate variable y here, and I can XOR them together and get an equation for the full thing, which only involves the inputs for the first round and the output of the last round and the intermediate keys. And if I keep doing this also with the next Sboxes and also across the next linear layers, then I can cobble together a linear approximation of just the input and the output, and I always need the intermediate values to essentially cancel out in the equation. So for example, I involve y4 in this equation and in this equation, so it cancels out when I XOR them. And this is the reason now why we can write it as conveniently as this, so we can assign an intermediate mask to each intermediate variable, because we know this mask needs to be, we need to have the same mask for the output of one round and the input to the next round. Otherwise, they won't cancel out if I XOR them. And if they don't cancel out, so for example, if I would have an equation using only y4 here at the output, but if I would need y3 and y4 at the next input, when trying to combine this together, I will have this leftover variable y3 in my combined equation. This makes it useless because y3 is something I don't know, I can't observe, I can't even guess and verify, so this will render my equation useless. So for that reason, I always need the same mask for output and the next input. And this means I can write down such a characteristic of masks in just the same way as I write down a characteristic of differences. And the difference is just that we don't mean differences now, we mean a selection of intermediate bits that happens twice and thus cancels out. And additionally, this mask also needs to involve some of the intermediate key bits, but in very many ciphers, these intermediate keys are derived linearly from the main key. So in that case, all of the intermediate things here can also be translated into equations of the full key. I don't, however, always need that. We'll see it a bit later. So even if I have a cipher with a nonlinear key schedule, I can still work with it, and we will see how. The main thing is that this is a constant. So if I do many evaluations, they always take the same values. So I can also handle them like constants, essentially. Okay, now there's one big question. We might know now what the bias or the probability or whatever of these two intermediate Sboxes is, but how does this combine into a bias of the combined equation that I've built here? So let's write down what we know and let's see if we can find out what we don't know. What we do know is that the first approximation has a probability of 1/2 plus some first bias epsilon 1. And I can read off this bias from the linear approximation table. It's simply the entry of the approximation table divided by the number of input values. So it's 1/2 plus 4/16. So the bias is 4/16. And the second one, I can also check that in the approximation table, we saw that the entry was -4. So the magnitude of the bias is the same, but this one has a positive sign and this one a negative sign. Okay, so this is what we know. What we don't know is what the combined probability of this entire equation down here is. And now this entire equation is actually correct in two possible cases. Namely, if both of the approximations for the first and the second Sbox are correct, or if they are both wrong. So if they are both wrong, each of them produces a 1 as a result, but if I XOR the two ones together, I get also a 0. So in other words, the combined probability is not just the first probability times the second probability, but additionally also 1 minus the first probability times 1 minus the second probability. Now I can multiply that out, blah, blah, blah. I can also rewrite it in terms of biases afterwards. And if I do that, what I get as a result is that this probability that I get equals 1/2 plus 2 times epsilon 1 times epsilon 2. So the new bias is 2 times the old bias 1 times the old bias 2, instead of just the product or something else. And this very important insight is called the piling up lemma, because the individual probabilities sort of pile up. And it can be formalized like this here. So if we are looking at independent Boolean expressions, this is a tiny little assumption that we made previously, namely that these two equations are correct independently of each other. Anyway, let's assume that they would be independent. Then each of them has their own independent probability of being correct. And if I now XOR not just 2 but n of these equations, for example the equations of each of the n rounds of the cipher, then the probability that this combined equation is correct is 1/2 plus 2 to the power of n minus 1, where n is the number of approximations I had, times the product of all the biases. And here we can now see why the correlation is a bit more comfortable than the bias to work with, because if I write exactly this equation in terms of the correlation, the result is simply that the total correlation of my equation for the full cipher is simply the product of all intermediate representations. So by having this factor of 2 already in the bias here, I get rid of this extra term here, and I also don't need to write down this probability-oriented 1/2 thing. So in total, if I know the individual correlations, just multiply them together and I get the full correlation. So this is why the correlation is often what you want to use if you look at the full cipher. Okay, so far for the theory. Let's have a gulp of water and then look at an example. And this example is the 4-round round-reduced version of the cipher present. You will notice that this looks very, very similar as the toy cipher in the previous lecture, but it's actually a real cipher. And it's also a relatively good one in the sense that it has a very low area footprint in hardware. But its security margin is a bit slim. Okay, so let's have a look at just 4 rounds of it. The full thing has something like 31 rounds or something. Okay, so we have these Sboxes, which are the same 4-bit Sboxes that we saw so far. And the linear layer is simply a reordering of the bits. So let's try something very simple. Let's try to say we want to have a good approximation for one of the Sboxes in the first round here. And this is just one I took from the linear approximation table. So it's 1100 to 1000, in other words, C28. This is just one of the good ones that I had in the table. And if we look at the values in the table, it had a plus or minus 4, meaning that the bias is 1 divided by 4, so 4 out of 16. And if I want to compute the correlation, this is simply double the value, so it's 2 over 4, or I'm writing it here as powers of 2, so it's 2 to the minus 1. I'm writing it as powers of 2 because powers of 2 are very easy to multiply together. You will notice here that I didn't write down anything for all of the other Sboxes. I did that for a very similar reason as we usually have when we look at differential characteristics. There we also like best those characteristics which have just one active Sbox. This is exactly such an active Sbox, and all the other Sboxes here which are inactive are actually also correct. This is the trivial approximation. We're approximating none of the input bits in terms of none of the output bits, which is totally correct. So this is just the equation 0 equals 0, or however you like. So this is fine. We can't use this 0 to 0 for all values because then we wouldn't learn anything about any input bits, so we need at least some bits active here. But it's okay to have just one Sbox. This also has the nice property, which is why I chose it, that it only has one active output bit. And we can now simply follow this output bit through the linear layer. So if the linear layer is as easy as here, I don't actually have to mess around with writing down the matrix and taking its transpose and so on. I can simply look at the picture and see that having an equation about this bit is the same thing as having an equation about that bit. Or in other words, I can just write down the mask here. I could also look at a different start with 2 active Sboxes. Why is that interesting? Because then for this Sbox here, I would have the same mask that I already know about. So I already know about one possible output mask here. Let's have a look at what happened here in the numbers. I've written down here the biases and correlations of all these Sboxes. So the very first Sbox had correlation of 2 to the minus 1. The second Sbox, since it's using the same masks, also has the same correlation. And the last one here again has the same correlation individually. I can continue doing that and so on. And at some point I'm interested in looking at the overall bias of this approximation. And as we saw on the previous slide, to get the overall bias, I can simply take all the correlations that I have and multiply them up. So 2 to the minus 1 to the power of 5 is 2 to the minus 5. And if I now translate this back to biases, then I also get a corresponding bias. Okay, let's have a look at now how we can use this for key recovery. For this, the cost of doing a key recovery attack is going to depend on exactly this correlation that I have here. So the correlation of an approximation, we already saw that it can be represented in several ways. One of them is the one how we defined it. So it can be written as 2 times this bias. I can also write it in different ways. So for example, if I look at how the bias was defined and put the definition back in, what I get is the correlation is also equal to 2 times the probability that the equation is correct minus 1. Or alternatively, I can also write it as the probability that the equation is correct minus the probability that the equation is wrong. Or, now this is a bit of a bigger step, I can also apply a sort of a Fourier transform to this, and I get this funny little representation. So I can also write it as 1 divided by 2 to the power of b, where b is the bit size of the function, times the sum over minus 1 to the power of always this equation here, so the value of this left-hand side of the equation. So if this is 0, then I get a 1. If it's 1, I get a minus 1 as the total result here. So in other words, each summand here is either 1 or minus 1. So if I sum them all together, I get exactly the sum of these values minus the sum of these values. And since I'm looking at probabilities, I still have to divide it by 2 to the b. So this is an alternative representation that is also useful sometimes, but most often not. Let's now see how the key comes into this, in order to better understand how the key recovery attack then works. So let's have a look at a full round block cipher, and what we want to have now, or what we can get if we follow the strategy that we saw so far. We can get an approximation for the full cipher, meaning some equation, a 1-bit equation that links a mask times the input plus a mask times the output plus a key mask times the key. And if I restructure this equation, I can also rewrite it as an XOR of some known values equals the XOR of some unknown values. And what changes about this equation if I look at a different key? The only thing that changes is the sign of the correlation in this approximation. So changing the key could correspond to XORing a 1 essentially here on the right hand side. So that means everything is correct turns into everything is wrong, and 5 cases are correct turns into 5 cases are wrong, and so on. Meaning it changes the sign of the correlation. And what's now interesting is if I leave out the key. So since the key changes only the sign of this correlation and does not change the amplitude, at least not under a couple of assumptions, then we get this equation here, which should have more or less the same amplitude. Now there are a few caveats that don't actually make this true in general, but it would still be interesting to look at this term here in isolation. And there is now a very famous algorithm for how we can use this to learn more than just one bit of the key. And the strategy is going to be somewhat similar to differential cryptanalysis key recovery. I see that there is a question. I will get to that a bit later maybe. I actually don't see it on my phone yet, so it will have to wait a bit. Let's hope that this refresh it later. So let's see if we have a slide where we can actually read the text. So the question says, choosing the masks for the first layer seems to somewhat limit the following options. Is there a way to choose good masks in regards to the following layers or trail and error? So this is a question that harks back to the example here. And the question asker observed correctly that in this picture here, I went about this very naively. So I just set some mask here and then just derived the best choices for the rest. And this works good enough in this example, but of course it's not perfect because there could be a different input mask that gives a better characteristic afterwards. So this is a very good point. The good news is that I can use very similar mechanisms for finding a good pattern as I also use for differential cryptanalysis. And one of these examples is the mixed integer linear programming that we saw last week, 2 weeks ago. So what I can do, for example, is I can describe all possible transitions of the Sbox here with some equations, and then try to find a solution for this equation system that minimizes, for example, the number of active Sboxes. Which of these technique works best, so whether it works best to just look at the cipher, recognize the structure of good characteristics and then do something manually, or whether it's better to use an automated tool like MILP solver, that depends a lot on the structure of the cipher. And we will see later that some ciphers actually allow to argue in a theoretical sense about the best possible characteristic, similar to the case we saw for the AES. And in those cases, it's actually very easy to characterize the best possible linear characteristics. But in the present cipher here, this is not so easy. I can give you a little spoiler. The characteristics I've shown here are actually very similar to the best possible characteristics. And you will need to do something similar for the exercises, and your solution will look very similar to what we're seeing here. I also just noticed that I misread one of the numbers here when I explained this slide earlier. So earlier I said 2 to the minus 1 to the power of 5. This is not exactly correct because we have a 2 to the minus 2 here. So this is a worse Sbox transition. It's great because it has just one input and one output bit, but it's worse because the correlation is worse. And this is why the correct total correlation here is 2 to the minus 6. And this also makes it compatible with the 2 to the minus 7 on top here. So it must be twice that value. So thanks for the question, allowing me to go back to that slide and fix that. If you try to play around manually with this thing for your exercises, good strategies are always looking which transitions you have that have few active input and output bits, because in case of present, the fewer input and output bits I have here, the fewer active Sboxes I have in the previous round. So that's one thing to aim for. And then the higher correlations are also one thing to aim for. Okay. So let's jump back to where we were. That was somewhere here, I think. Yes, I was just starting to talk about Matsui's algorithm. So how does that one work? It assumes we have an approximation like I've discussed so far. So some masks for the input, ciphertext and key. And for the sake of the example here, let's assume it has a positive bias, but it will also be okay if it had a negative bias, as long as the bias is not 0. And let's assume we have a couple of ciphertexts, of known plaintext ciphertext pairs at our disposal. What we want to do now is we want to evaluate for these plaintext ciphertext combinations how often they satisfy our equation. If it has a positive bias, we would expect that it satisfies the equations more often than not. But of course, this depends also on the key. So the key here, it's a constant, meaning it's the same key for all of the plaintext ciphertext combinations that we look at. So it simply changes the role of correct and wrong ciphertexts, but it doesn't change how far this is away from random behavior. So it's either correct more often or wrong more often, but how much more often does not depend on the key value. By the way, I see just now that my mic is a bit misconfigured. It might be a bit louder than usual. If it's too bad, let me know and I try to tune it down a bit. Okay, so we have this combination, we have many pairs, and we want to now measure how often our equation is correct. And this is going to be done as follows. So we are not going to have just one counter, but two counters, one for the correct cases and one for the wrong cases. And now we go through all of our plaintext ciphertext combinations. If the value of plaintext mask times plaintext plus ciphertext mask times ciphertext is 0, then the equation is correct. So I count up the counter T0, and if it results in 1, I count up the counter T1, which counts the incorrect cases, so to say. Now, what do we learn from this if we look at it at the end? If T0 is bigger than T1, meaning this equation here was correct more often than wrong, then we can assume that the XOR of these key bits was actually 0. This is because this is the original equation here. It includes the key bits, and we said it has a positive bias. So this means that this full equation should be correct more often than not. And if we just leave out this part here and it's still correct more often than not, then this means that this value here was probably originally 0. And vice versa, if the counter for the 1s is bigger than the counter for the 0s, then this probably means that this here was originally a 1, so that the data is actually compatible with what we know about the bias and the equation. So this is a very easy algorithm. There is one downside here, and this downside is that from a lot of data and this one good approximation, we only learn one bit of key information. And if we want to learn more of the key, we actually need more than this one equation, more than this one linear approximation. So this is bad, because we need to find more things, and we can't just exploit one good characteristic that we have. So that's exactly what is written down here. What's the advantage? Well, I directly learn some key information, which means I can directly use it to attack confidentiality. There is, however, a cleverer algorithm, because what this one here has not exploited is how strong the bias is, or how much different it is from 0. And we can take advantage of this information if we set up an attack similar to the key recovery attacks in the differential case, where we have an approximation not for the full cipher, but just for most of the rounds, like all rounds except the last one. In that case, we can take all our data, all our known plaintext pairs, plaintext ciphertext combinations, for each of them, and for each possible candidate of the last round key, we can decrypt, and we can count how often is my approximation correct and how often is it wrong. So for each pair and for each key candidate, I need to evaluate this loop. And for each key candidate, I collect again these counters, how often it's correct and how often it's wrong, across all plain texts. And now I look at the result at the end. So for each of the key candidates here, I will then have a number of upvotes and a number of downvotes. So a T0 counter and a T1 counter. Now what do I expect for the right key? For the right key candidate, what I do expect is that my evaluations here, my experiments, will essentially replicate the behavior of the equation and the bias that I expect. So I expect this data to have the right bias, which is a big bias. That's how we chose our correlation. So in other words, there should either be much more or much fewer correct examples than wrong examples. So if I look at these cases here, for the first key there were exactly the same number of T0s and T1s. Here it's mostly the same, just one different. And here I actually have a lot more, so T0 is a lot larger than T1. So a good guess would be that this is actually the correct key. In reality, of course, it's not just such small numbers, but these are going to be huge numbers. So the sum here is the same as the number of plain texts that I have. And this number, to be really clearly distinguishable, needs to actually be very large. It's proportional to approximately 1 divided by epsilon squared, where epsilon is the bias of the full equation. So this is, it's not like 1 divided by p in the differential case. Here we actually have a square with respect to this bias here. Okay, so that's the basic algorithm. This is called Matsui's algorithm 2. And it looks for the key which has the highest difference between T0 and T1. How could we implement this in the example? So this is the same example as before, 4 rounds, except now we're not going to look at an approximation for all rounds, but just for the first 3, and we're going to use the last round for key recovery. So this means that our bias for up to here is now, this here together is 2 to the minus 5 as a correlation, which corresponds to a bias of 2 to the minus 6. And how could I now check this? How much do I need to guess to verify this bias? I need to know these 4 bits here. I can read that off directly from the plain texts. And I need to know this 1 bit here to evaluate my equation. So what I need to do to learn this bit is I need to guess 4 bits here so that I'm able to decrypt the last Sbox. Plus, I would also need to guess 1 more key bit here so that I actually know the value. But since I'm using not the direction of the bias in this attack, but just the strength, I can actually ignore that part here because it won't change the result, the number of corrects or incorrects. Also, it won't change the difference between the two. Okay, so I need to guess, depending on how you do it, 4 or 5 key bits to learn this bit here, and I repeat that for all data. So since the bias is 2 to the minus 6 here, I will need something in the order of magnitude 2 to the 12 ciphertexts. For good measure, it should be a bit more than that. So like in the differential case, we have a constant in front of this order of magnitude. So probably something like 2 to the 15 or 2 to the 18, something like that. This is the number of plain texts I need to collect. And for each of them, I need to evaluate this with 4 key bits here. So if I look at the complexity of that, I need to multiply those complexities. So I have something like 2 to the 4 times 2 to the 18 or whatever as a complexity for exploiting this characteristic here. The good thing is that this complexity is now measured in known instead of chosen ciphertexts or plaintext, because I don't need any specific properties. I can use any plaintext ciphertext combinations that I can get my fingers on, but I do need to know both input and output. So it's a known plaintext attack. So what are the advantages and disadvantages of this approach? One thing that's much better than the first approach is that I need an approximation not for the full cipher, but just for the round reduced cipher, for example, r-1 rounds, I do learn more of the key information at once, because in this case I learn not just one bit of key information, but I learn 4 bits of key information from executing this attack. So that's another advantage. It's still a known plaintext, known ciphertext attack. It should read plaintext here because I always know the ciphertexts. What are some disadvantages? One very big disadvantage for the complexity is that I cannot filter out my candidate data in advance. In the differential case, I can very often look at my plaintext pairs and ciphertext pairs, and I can already rule out some of them. They cannot have originated from the correct characteristic because they have, for example, some differences in the output where they should be none. By kicking them out earlier, I reduce the total attack complexity a lot because I only need to look at the remaining data. That's unfortunately not possible here. I really need all the data. So the total complexity of the attack is higher. And compared to the algorithm 1 before, I need to guess more key bits, which increases the complexity again. So the number of active bits in the cipher or 1 round before the ciphertext is also a very important metric to judge how good a characteristic is. So now are some more details about how much data we need. I've already given you a spoiler of how much it is approximately. It's more easily written down using yet another approximation for the bias, namely the squared correlation. The squared correlation is nothing else than the correlation we already saw and squaring the result. So far so easy. Why do we do this? Because we saw that the complexity depends on the squared bias, or in other words, on the squared correlation. And if we know this correlation, then we can distinguish this from the random case, so from the wrong key candidates, with a complexity of approximately 1 divided by the squared correlation of my approximation that I have. If you want to have more details, so there are formulas very similar to those we saw in the differential case. I don't know how often I've been saying it in this lecture, but it's really very often very similar between the two. And there you get a similar complicated formula using the normal distribution and some other factors like what success probability do I want and so on. I can evaluate in detail, but you can also just try it out. So if you have a specific attack that you want to do, you can simply look at how strongly the different counters for the different key candidates are different, and as soon as there is one clear winner which is clearly above the others, you're done. And even if there are 5 key candidates which have a similarly high chance, you might just consider all of these and brute force the remaining options. In all of what I've explained so far, there were a number of assumptions or caveats that you should have in mind. Why this attack doesn't always behave exactly like you would expect. And one of these is the so-called hypothesis of fixed key equivalence. What this means is that this squared correlation of my alpha and beta, so my input and output mask, the actual correlation does depend on the key, and it's very hard to evaluate in practice. So this is like the difference between looking at a characteristic, a differential characteristic, and looking only at the differential. It's something similar here, which I'm also discussing below. So the exact behavior is going to be slightly different from this predicted correlation. The correlation is just the average across all possible keys. And what you assume here is that if you attack a specific target key, it behaves approximately like an average key, but this won't be true for all keys. So there will always be some outliers which have a different correlation. And the second thing, which is also related to the first thing, is this linear Hall effect, which means that there might be several characteristics, so several paths through the cipher that correspond to the same linear Hall. Linear Hall being just the alpha and beta masks. And so this means if they have different biases on their own, this has an effect on the linear Hall, so on the total correlation. And actually this relationship isn't even as easy as in the differential case. In the differential case, we knew that there may be multiple characteristics, and the sum of their probabilities gives the total differential probability. So if I have one good characteristic, then the differential is going to be at least as good. So if you describe a theoretic attack, you can always say the attack might be even more efficient, but it's at least this good. You cannot do this in the linear case, because the individual characteristics might be both better and worse than the actual linear Hall for a specific key. What we often assume, and what is to some extent true for some ciphers, is that there is one dominant trail, which means one characteristic, one trail through the cipher, which is much stronger than all the other ones. So its behavior dominates the behavior of the overall linear Hall, and all the characteristics with smaller biases don't change it that much. In that case, if there is such a dominant trail, then the probability or the bias of this trail is a good approximation or a good prediction of the overall behavior. But this isn't always the case. So this is something you might also observe in the exercises, that your measured effect doesn't match exactly what you expect. You will also see that for the example in the exercises, you can find several different characteristics with a similarly good probability. And depending on which one you pick, you would predict different behavior for what is actually the same thing. Okay, so this means what we need in practice is a thorough evaluation. So if you claim an attack, you should try to execute or practically evaluate all the parts of the attack that you can, in order to gain some confidence that the predicted behavior, what you think is the correlation, is actually approximately correct for many of the keys. So for example, you could run your attack or part of your attack on many target keys and see whether they behave approximately as expected. Okay, so with all of these dire warnings, let's have a look at some more ciphers, and let's look at how we can argue security against this attack, even if we can't guarantee it, for the reasons we saw on the previous slide and more. So we again have these two roles that we want to play here. So the two heads. We can have the designer head, where we want to ensure that there are no good approximations, which means there are no approximations whose corresponding data cost would be feasible. So a good approximation is one whose squared correlation is much better than 2 to minus the block size. This would allow me to distinguish the behavior based on as much data as I can get, because I cannot get more data than 2 to the block size many blocks. That's the maximum of data I can get. And if the correlation is worse than that, I simply cannot collect enough data. So not only not practically, but absolutely not, because there is not more data to look at. If we're wearing the attacker hat, then we want to find one good approximation and gain some confidence that this actually behaves as we expect. So since it's very hard to show that there are no good approximations in terms of their overall correlation, what we can do is we can show that there are no good characteristics. if we make the dominant trail assumption, then a strong strong approximation would also correspond to a strong characteristic, and if there is no strong characteristic, there is no strong approximation. How do we get there? We see, like in the linear case, we need to ensure two things. We need to have a strong Sbox, where the individual entries in the linear approximation table aren't too high, which means each Sbox incurs a significant cost. And on the other hand, we want to make sure that as many Sboxes are active as possible, because the combined correlation, the multiplied correlation of all, the squared correlation of all the Sboxes determines the squared correlation overall. And in addition to these, when I design a cipher, I also want to plan a sufficient security margin, which compensates for the rounds I would cover with key recovery, potential effects in the cipher that I didn't foresee, like for example, not just one dominant trail, but several good trails which combine their effects, or the fact that I might have multiple good approximations that I can combine. So for all of these reasons and assumptions, I can't prove that something is secure against the cipher, but I can show that it would be very hard for an attacker and probably not possible, because if there are no good characteristics, how should the attacker start? And if I assume additionally that there are dominant trails, then this would also imply that there are no actual good good approximations. Let's have a look at the cipher we've seen so far, but at the full thing, and how the designers argued that it's secure. So what they did prove is that any fork around characteristic has a bias of at most 2 to the minus 7. We saw one actual example of a 4-round characteristic which does have a bias of exactly 2 to the minus 7 earlier. If you write this down in terms of squared correlation, this is a squared correlation of 2 to the minus 12. And how did they do it? By manually describing all possible patterns. Patterns of how many active Sboxes there are and what their bias is. And if you're interested in how they did this, you can have a look at the design paper of Present. There they simply describe it. So they enumerate all the cases, like if I have just one active Sbox, then either I have 2 Sboxes in the next round active, or I need to have a bad probability, etc., etc. So this is a manual argument. And the total thing has 31 rounds. So if we look at a multiple of 4, if you look at 28, which is 7 times this behavior, then as a result we get that the combined bias is at most 2 to the minus 43, or if I square it, definitely the data complexity would be much higher than 2 to the 64. Or if I do it in the correlation, in terms of the correlation, the computation is a bit easier, so in the squared correlation, because if I have 2 to the minus 12 for 4 rounds, then I have 2 to the minus 12 times 7 for 28 rounds at most. And this is 2 to the minus 84, which is definitely a lot smaller than 2 to the minus 64. That's again the data I could be able to collect. However, so this reasoning tries to argue why it's probably hard to attack the cipher. So assuming even if I would do a key recovery over the remaining 3 rounds, still I would need way more data than I have. However, what the designers underestimated is how different the probability of the best characteristics is from the actual combined approximation. So there is a very strong linear Hull effect, and if I use multiple approximations, it incorrectly says differentials here, it should be approximations. And if I put a lot of effort into the key recovery to cover not just 1 or 2 rounds, but more rounds, where I always guess the key, then I can target up to 28 out of the 31 rounds. So this is a very recent result that was published, I think, last year or so. So this means that the remaining security margin of this cipher is very slim against this kind of attack. So if we would design it with this knowledge afresh now, we would probably choose a higher number of rounds, because this is just a very small remaining security margin. So that's the case of present. Let's have a look at the AES. And let's have a look at how valid approximations look like there. This picture will look familiar to you. This is a description of possible patterns for differential characteristics, but at the same time is also a description of potential patterns for linear characteristics. So if each white square here marks a cell of AES with a zero mask, so no active mask, and each colored one maps some sort of active mask, then I can get a similar number of active Sboxes as in the differential case. So for example, if I look at a mask which corresponds to just one of the cells at the plaintext, this means it corresponds to a mask at the input with one active cell at the input to sub-bytes. If I have an active input mask, I also need to have an active output mask of sub-bytes. Shift rows just rotates this around. And now mixed columns, this is the interesting step. Mixed columns actually has the same lovely property for differential approximations as for the linear case. Namely, its linear branch number is the same as the differential branch number, which is 5. Which means if I have just one active cell at the input, all of the output cells must be active. If I would have 2 here, it would be at least 3 here, and so on. So if I start with just one active cell, I would go into the second round with 4 active cells, and so on, which would blow up to a fully active state, and then potentially reduce again to this one here. I've now argued here how it looks like if I start from one active cell. Of course, I could also start from a different input pattern, but because of the arguments, because of the properties of mixed columns, and by using either the same theoretical arguments with super Sboxes as in the differential case, or if you don't want to think, you use the same mixed integer linear programming model as in the differential case, you also prove exactly the same bound, which is the bound of 25 active Sboxes over 4 rounds. And the Sbox itself is relatively strong against linear cryptanalysis. So it has a maximum squared correlation of at most 2 to the minus 6. So in total, any approximation of 4 rounds already has a squared correlation of 2 to the minus 150 and is thus not directly exploitable. So AES has a very generous margin against linear attacks because even 4 out of the 10 rounds are already far beyond what we can cover with linear cryptanalysis with the given amounts of data. Okay, so coming to the question that you already asked earlier, how do I find these characteristics? Well, either I make arguments by hand. For example, if I have strong structural properties, I can get strong bounds like in the AES based on the mixed columns behavior. That's a high-level argument. If I don't have such strong structural properties, I can try on a smaller scale, like in present, where I can manually evaluate and enumerate possible patterns and put bounds on those. Or with the computer, I can use any off-the-shelf solvers or also dedicated tools. So for example, a couple of years ago, we also built such a tool at the Institute. Okay, so let's get to the conclusion of the lecture part. Linear cryptanalysis is a very powerful attack. It's a statistical attack and one of the 2 most important attacks. So whenever there's a new cipher, we need to argue why it's secure against this attack. There are many parallels to differential cryptanalysis. I've mentioned many of them today, but not all of them. So what do these parallels include? So visually speaking, I have the same sort of table describing the Sbox, because I have the similar concept of masks, which are like differences. I can draw characteristics, just as in the differential case. I describe a statistical behavior, and I make statistical probability-based predictions, as in the differential case. I can do similar key recovery approaches, and so on. However, there's one important difference. It's a known plain text attack. So this is usually easier to execute than the chosen plain text attack, like in differential cryptanalysis. If I want to attack something, I need to find a good linear approximation, which I usually do by finding a good linear characteristic first. And this will include in particular this approximation of all the nonlinear steps, so of the Sboxes. And if I have such a very good linear characteristic, and thus assume I have a good linear approximation for the full cipher, then I can use this algorithm too, which counted how often is it correct, how often not, in order to distinguish between correct and wrong key guesses for the last round. And as a new cipher, you always need to argue why this attack is not applicable. Okay, which questions do you have before we go into the exercises? Okay, nothing urgent, it appears, so let's head on to the exercises. If something still comes to your mind, you can of course always ask, and I'll revert back to this slide here, and we can discuss your question. So let's have a look at the second assignment sheet for the exercises, which is called Symmetric Analysis, and will cover the lectures of the second half of this course. In terms of timeline, as you are probably very well aware, we just finished the previous assignment. So before I start going into the next one, I also want to have a few comments on this, and in particular on the assignment interviews for the first task. I will also send you an email with the details in case you don't watch this lecture in time. For the next assignment, the timeline is the following. We are publishing the tasks today. They're already on the website. You again have a bit more than a month to work on them. So the deadline is at the beginning of June, the 10th of June. And a week before that, or 2 weeks actually apparently, because there's probably a holiday in between, we again have a question hour right after the lecture. But of course, as usual, I'm also available right after the lecture, so either me or Markus, right after the lecture on Discord. Though I have to say this hasn't been used a lot so far, so apparently there's not a lot of need for questions. Okay, so so far for the timelines. Now let's get back to that first assignment for a bit first. And I also have a few questions for you here, in order to get some feedback on how well that went. So, in particular, I was wondering, we haven't evaluated the submissions in detail yet, so I was wondering how much did you actually solve? So to what extent did your team solve each of the tasks? Nothing at all, or did you completely finish all the subtasks? How did it go? So far I see only, I think that's one very successful team. Looks like all of you actually tackled everything, at least all of those who are watching and participating at the moment. Okay, Some other teams didn't completely finish, so that's probably something like 2/3 or so of the last task. Let's just wait for a second. Okay, so it sounds like despite Corona, you were mostly very motivated. So that probably also means you start with a lot of, well, not exactly bonus tasks, but a good pile of points for the next task. Since you know you don't need to acquire the full total of points to actually get counted as 100%. Okay, so this is how much you were successful. I was also wondering, how hard did you find each of the tasks? So was it very easy for your opinion, not a lot of work, or very hard, lots of headaches and long hours? How did you feel about the individual tasks? Okay, so you're collaborating to draw a very nice linear line through this here in terms of your average perception. So it looks like there is most disagreement about the middle one, from very easy to moderately hard. Of course, I didn't specify when asking the question whether you're supposed to scale with regards to the points it gave. I just asked, but anyways, it looks like none of these was too horrible. That's good to know. Maybe the tasks are even a bit too easy, who knows. Okay, but then again, maybe it's not representative if I'm asking during the lecture. Okay, thanks a lot for that. So let's now come to these assignment interviews. So as we announced in the beginning of the term, we will have interviews or Abgabegespräche for each of the 2 assignment sheets separately. We do have already one main slot that we want to use for these interviews, and that is next Tuesday already. So this is very soon, and it's in the afternoon, sometime between 12 and 3 or something like that. Please sign your team up for one of those slots. So there is if you go to the course website, there is a clickable doodle link behind this, but you will also receive this link later today by email. If none of the slots are feasible for you, for example, because it collides with an exam or whatnot, contact us or me directly so that we can agree on a separate slot. So either by email or by Discord or however you prefer. But if it's feasible, it would be easiest for us if you choose this slots on this Tuesday. Okay, during the interview, these are going to take approximately 20 minutes, and the main goal there is to just go through your tasks, make sure that for each part at least one of you has an idea of how it works. Ideally, you also know what your partner did, but of course we don't require that you know all the details about every line of code from your partner. But you should have a general understanding of what approximately happens where and what the main challenges are in the task. So we'll go through those. If there are things that don't work, we can also try to debug a little, but we don't have too much time in the 20 minutes. So we'll just discuss your solution. If you have any questions, feel free to ask. For the seminar, we also have that upcoming. So we waited with the announcement to see who actually submits something for the first exercise task. And currently it looks like 2 teams who signed up for a seminar also submitted the first task. This would mean that we actually have one date, namely on the day of the submission for the second assignment sheet, where we don't have any seminar talks. And our proposal is to have each one of the 2 seminars on its own day, so one on the 17th of June and one on the 24th of June. If you don't like this assignment, so if you're one of these groups and don't like it, you want to swap or whatever, just talk to us and each other to agree on something. So in theory, everything is possible. You can choose any of these 3 slots for your talk. We can also have both in one week, though that will probably be pretty exhausting for all of us, however you prefer. If you are the team who signed up for a seminar but didn't hand something in for the first assignment, please let us know whether you still plan to do the seminar or not. And we'll assign you accordingly. And we also published, once this is completely fixed, we'll also publish it on the website so that all of you know when to join for something and when not. All of these talks are going to be done in WebEx, so I will host a meeting there. You can join, share your slides. If you're presenting in a pair of 2, then you can do this 2 ways. So either if you have a very clear separation between your parts, you can do it like one person presents the first half of the slides, then you switch presenter to the other person who shows the second half of the slides. Or if you're changing a bit more, you can also have one person who does some half of the fragments of the talk to handle the slides, and the other one will then need to tell them when to forward the slides. So this is, as a listener, maybe a bit inconvenient, but try to make it work for you. If you are physically living in your vicinity anyways, then you can also team up in front of one PC or so. We're currently planning to still do this virtually, even though I hope by end of June the situation in terms of Corona will be much more relaxed than now. Yeah, so unfortunately I think we won't be able to do the physical presentations, but maybe you prefer the virtual ones anyway, those of you who are presenting. In any case, let us know if you want to change something, and please also contact us sometime soon to talk about the contents of your talks. So independent of whether you've already prepared something or not, or already have an idea what you want to talk about, please just send us a mail. Probably I will supervise one of the 2 talks and Markus will supervise the other one. And we can then discuss in detail what you want to do or what you could do. And this is also a reminder that we hope to receive your final draft for the presentation approximately 1 week before your actual presentation slot for final feedback. Okay, now for something that probably possibly interests a bit more of you than the seminar slots, namely the tasks for all of you. And again, we have 3 tasks, an easy one, an intermediate one, and one which is more effort. And the first of these targets the AES, and it's a square attack on this cipher. So the square attack is a sort of, but not really, differential attack that you saw in the previous lecture, lecture number 7. And to refreshen your memory, this was the attack where you looked at sets of ciphertexts of, in case of AES, 256 ciphertexts, where most of the ciphertexts are identical for all of the cases, namely they are constant, denoted by a C here, but there are some cells which are different. And if you look at the lecture again, you see how it was possible to then say something about these sets after up to 3 rounds. So after 3 rounds, you still know that the outputs are what's called balanced. So if you XOR them all together, you get 0. And this is the property you want to exploit. You can, and this is the task, do a very simple key recovery attack, byte by byte. Or if you want some bonus point, you can also attack not 4-round but 5-round AES, where you need to guess more of the key material. So these are the 2 subtasks. First, to just evaluate this balanced property in itself, which essentially consists in getting your AES up and running, getting some functions to generate these structures, but should otherwise be very easy. And in the second step, you then use it for the key recovery of 4, or if you like, 5 rounds. The second task is about what we heard today, namely linear cryptanalysis of present. So you want to attack the methods that we saw to this cipher that we had in all our examples. And here we have 3 steps. The first thing to do is look at the Sbox of the cipher, compute the linear approximation table. You can verify your result based on the lecture slides, but please still do write your own code to generate it. And in this first step, you also need to find a good 9-round linear approximation. So this is more rounds that we had in the lecture, but you can use the patterns that we saw and these building blocks to find very good approximations. So you build a characteristic like this. You can do it in this naive way that I showed in the lecture, starting from what you think is a good input and then continuing. So that's the first step. The second step, which is a bit intertwined here, is that you should also try to evaluate the bias of your approximation. This is something you probably already want to do while generating it to be sure it's good. And we want you to verify it experimentally. Because as we said, in practice the behavior can deviate quite a bit from what you would predict based on your characteristic. So please check that first before you conduct the actual attack. And the actual attack is then the last step. So here you need to implement this algorithm 2 of Matsui to recover the key for 10 rounds of present. So this means 1 round of key recovery at the end. If you like, you can also adapt it and do, for example, 2 rounds of key recovery if you think it's more efficient, however you prefer. And this is worth in total 3 plus 2 plus 3 equals 8 points. And the sources I've listed here are, on the one hand, the specification of the present cipher, where you can already read some comments about what good characteristics look like. And on the other hand, the original linear cryptanalysis paper, where you can read up on the attack details if you like. However, be warned, much of the paper is busy with the peculiarities of the death cipher, which might be more confusing than helpful, even if the actual attack description is very nice and clear. And to work on this, so here is a smaller picture of just 4 rounds of the cipher, just to recall what it looked like. On the course website, we're also offering a full 10-round picture of this cipher for you to print out, and we're also including the TIX code, so you can recompile it with a different number of rounds or whatever you like. So this is part of a zip file, which also includes some other building blocks in case you want to make pictures of this step or the previous square attack, or also the Ketchak description. And Ketchak is a keyword for the last task, because there you are going to conduct a cube attack on Ketchak. Now, despite the similarity in name, the cube attack is not something like a higher dimensional version of the square attack. It's something pretty different. However, it's also a type of algebraic attack, and you will get to know it in more detail in 2 weeks' time. And what this cube attack is about is it also, so this is the similarity with the square attack, it also takes the sum of many, so of one intermediate variable across many cipher texts. And this sum is again supposed to be 0, but you're exploiting it in a very different way here. And specifically, this attack consists of multiple phases, offline and online. So first finding cubes and then exploiting them for equation solving. And the final task is to apply these principles to the 4-round Ketchak scheme. However, we're not going to look at Ketchak in the sense of the hash function, as you might know it, but we're going to look at an application to a MEC function based on Ketchak. Because all of this mostly makes sense when we're interested in recovering a key. So this is what you're going to do here. And to help you in this task, I've also included some cheat sheet information here on what ketchup looked like again. So you can try to draw it as a matrix like AES. However, then each of the values here is 64 bits long, and the Sbox is not actually within each Sbox, within each such block of the full picture, but across them. So for each row of the matrix state in the previous picture, and for each of the bit positions in there, you apply this 5-bit Sbox to get some 5-bit output. And the other operations in the cipher are something a bit related to shift rows, where you exchange all the position of the individual cells in your matrix representation. There is a rotation step which rotates each of these 64-bit cells within itself. So it takes this as a 64-bit word and rotates it. And we have this summing step which takes the sum of two columns and XORs it to the cells in between those. No worries if you don't understand it from this brief description here, and if you don't remember it from cryptography, you will hear about it again in lecture number 10. And the scheme you're then targeting uses this round function here for 4 rounds as the permutation f, and you're going to look at a MEC usage of this hash function, which means as an input you use not just the message, but you prepend the key. And if your message is very shorter than 1 block size here, then what this MEC effectively does is it simply applies this 1600-bit permutation to an input which consists of some zeros and the key and the message. And of this 1600-bit output, you select the first 128 bits as the MEC. And if you map this to the description on the previous slide, which had these 64-bit words named S0 to S24, then the key corresponds to the first 2 words. So in this picture here, that's these 2 words here. The message is in the next 15 minus 2 words, and the MEC at the output corresponds to the same positions as the key at the input. And to make sure that your mental image of this function agrees with how the attack works, here is an example of a cube. This is this particular type of structure that you'll hear about in 2 weeks, which works for just 1 round. And it's very simple. It's also a sort of equation, and here's the example if you want to refer to it. But this will make more sense after lecture number 10. So these are the tasks. Otherwise, the rules are pretty much unchanged from the previous time. You can again use your favorite programming language. You will again need implementations of the ciphers you're targeting. I have some links on the next slides that you might want to use. You will again need linear equation solving, at least for the Ketchak task. This is something you probably already found out how to do as part of the first assignment sheet, but you're definitely going to need it again here. If you want to integrate or use anything that's not part of the open source standard packages you would expect us to use, please ask us. The suggested thing is essentially just to use C or C++ with standard libraries, which should be pretty much sufficient. The only thing where this might be a bit more inconvenient is the Boolean equation solving. So here you can try to also reuse what you had for the first assignment sheet. Submission is the same as for the first one, so you make 1 zip archive per task, so A, B, and C, and upload them in the corresponding upload subtask in sticks. Again, please include a README. We might give you some feedback on the READMEs for the first task and maybe ask you to improve some aspects for the next one. But you will see that in the assignment interviews. Also, again, please include clear instructions how to run your code and or ideally and a makefile. So what implementations can you use to execute these tasks? For the first one, you will need an AES. One very obvious choice here is you can use the ANS-NI instruction set included in the more recent Intel platforms, which you can use to cobble together however many rounds of AES you need. You can also use a publicly available implementation, like for example, I've given an example link here, but there are really tons of implementations of the AES out there. For present, it might be easiest to implement the cipher yourself, or you can use the implementation that's available on the Lightweight Crypto website. And for Ketchup, there is an official code package which is very thorough, very efficient, but a bit hard to navigate. So this can be a bit overwhelming because they really have tons of different implementations of each of their ciphers, but there are a few standalone implementations which don't require most of the framework they have. And in particular, those standalone implementations have some functions which execute the core permutation. These are what you're after. So I hope this URL here is still correct. It might have moved somewhere in the package by now, but if you look at this for the standalone implementation and inside of that look for just the permutation call, then you're good. Don't use all of the additional code and framework around that, which implements all sorts of sponge variations and whatnot. You don't need any of that. Okay, some final hints that might help you. In all of the cases, it might be easiest if you start with fewer round numbers first. For example, if you try to tackle present, first test it with, for example, just a one round linear approximation and a one round key recovery, so that you see whether your understanding of the attack works out. In symmetric cryptography, very, very often, an error is just the source of some misunderstanding in how the bits are labeled or which parts to sum exactly. There's a lot that can go wrong there, and that can cost quite a bit of nerves. So this is not just limited to you. So even when I try to do something, I very often run into this issue, like how are the bits, the bytes encoded, which bit corresponds to which bit in the state, and so on. It can be messy. And it's easier to understand when you have just one round or so, where you still understand, for example, which mask combinations should definitely work out. It can also be helpful if complexity is an issue for you, to start working with a partially known key. So for example, in case of AES, assume that you already have all of the key except for one byte, and then just implement the key recovery for that byte, and then extend it to the full thing step by step. Pictures can be extremely helpful. As I said, there are some example pictures for you to use on the website. If there is something specific you need or something great that you did that you think the other teams might feel useful, just bring it up in the Discord and everybody will be grateful. And again, some of the tasks might run a little while, depending on how you implement it, what language you choose, and so on. If it's infeasible for the specified round number, try it with fewer first and then discuss with us and see whether the problem is some tricks that you need to do in the implementation or whether there's an error and so on. So in particular, I recommend to start early and not on the last day. Okay, that's it from my side. Let's see if you have any questions by now. Okay, not a lot going on here. So thanks a lot for joining today, and best of luck with the exercises. The next 2 weeks, the lecture will be done by Marcus. So I'll only see you again during your seminar talks, or if you show up for the question session at some point. So have a great evening and bye. Good luck with the exercises.